Hello everybody, in this video we're going to continue with Chapter 3, Sequences and Series, specifically 3.3, Geometric Sequences. So what would be an example of a geometric sequence? Let's start with, say, number 3, then the next term 6, 12, 24, 48, 96, etc. So this is a typical geometric sequence. Notice that we multiply by 2 to get the following term of the sequence, and this is what's called a common ratio R. Recursively, we can see that the nth term is equal to the previous term times the ratio. But what would be a non-recursive formula? Well, for these formulas, we would have to take the first term. So let's say 3. So notice that we get 6 by multiplying by 2, and then we multiply again by 2 to get 12, and then by 2 to get 24, and then by 2 to get 48, by 2 to get 96, etc. So what would be the pattern? Notice that since the sequence is 3, 6, 12, 24, 48, 96, etc., the first term would be 3 times 2 to the 0, then 3 times 2, then 3 times 2 to the 2, 3 times 2 to the 3, 3 times 2 to the 4, 3 times 2 to the 5. So notice that this is the first term, this is the second term, this is the third term, fourth term, fifth term, sixth term, and so forth. So what would the general formula be? Well, notice that the nth term would equal the first term times the common ratio to the power of the index of the term minus 1. Notice that 0 is 1 minus 1, 1 is 2 minus 1, 2 is 3 minus 1, etc. So this would be the general formula for a geometric sequence, and this one would be a recursive formula for any geometric sequence. So the next slide, we're going to find example 3.8, and it says for part A, find the geometric sequence with the first term 2 and a common ratio 3. So when they say find the geometric sequence, it means just write the sequence. So this would be 2 would be the first term, 6, 18, 54, etc., right? That would be the sequence. And if they want a general term or to describe the sequence, we would say that the nth term is equal to 2 times 3 to the n minus 1. For B, it says describe the sequence. So it starts with 3, then negative 12, then 48, then negative 192, etc., right? So this obviously has a common ratio of negative 4. So the common ratio is negative 4, and we know that the first term is 3. Therefore, the nth term is simply going to be 3 times negative 4 to the power of n minus 1. Now notice that when the common ratio is negative, the terms of the sequence alternate in sign. For C, they ask us to describe a sequence which is 1, 1/2, 1/4, 1/8, etc. So here it's obvious that the common ratio is 1/2. The first term is 1. So the sequence would be, the nth term would be first term, which is 1, which we won't write, and then 1/2 to the power of n minus 1. For part D, they want us to graph the sequence a sub n is equal to 1/4 times 3 to the n minus 1. Now this, if we do it graphically, we should do it as a function, right? So we'd say that y is equal to 1/4 times 3 to the x minus 1. So this graph is obviously going to be exponential. We're going to take a look at it. So here we are with the GDC, and we're plugging it in as y equals 0.25 or 1/4 times 3 to the power of x minus 1. So we hit the graph button, and there you go. You get an exponential function. So these geometric sequences can be modeled using exponential functions. Okay, so now we continue with example 3.9, and it says at 8 a.m., 1,000 milligrams of medicine is given to a patient. At the end of each hour, the amount of medicine in the patient's bloodstream is 60% of the amount present at the beginning of the hour. A. What portion of the medicine remains in the patient's bloodstream at 12 noon if no additional medication has been given? So this is obviously a geometric sequence. And the first term is going to be 1,000, the initial amount of medicine, and the common ratio is 60%. So this is going to be 0.6. Therefore, the amount of medicine present in his bloodstream would be equal to 1,000 times 0.6 to the power of n minus 1, where n is the time in hours. So here you have to be careful with the time, because the first dose is at 8, then it starts gradually going down. So 9, 10, 11, and 12. So 12 is the fifth term of the sequence. Therefore, at noon, we would say that it's 1,000 times 0.6 to the power of 5 minus 1, or 4, and then just plug this into the calculator, and you're going to get 129.6 milligrams. For part B, it says, if a second dose of 1,000 milligrams is given at 10 a.m., what is the total amount of medication in the patient's bloodstream at 12 noon? So we know that at 12 noon, he's going to have this left after his first dose. But then if he's given another dose at 10 a.m. Of 1,000 milligrams, and we know that 10, 11, 12. So this would be the third term of that sequence. So that means that we would have to add an additional, this would be 1,000 times 0.6 to the power of 2 in this case, 3 minus 1. So this to the power of 2, and that's going to be an additional 360 milligrams. 360, but we have to add what we knew from before he would still have remaining in his bloodstream at noon. So this would be plus 129.6, and we're going to get that the answer for B is 489.6 milligrams. In the next slide, you're going to find some notes about compound interest. Compound interest is an example of a geometric sequence, and we're going to see that through this table here. A sub 0, or the first term, is equal to P, the principal or initial amount. R is the annual interest rate. R is a percentage, so it's written in decimals. T is the number of years. So notice that when you make a deposit, let's suppose you're putting money in the bank and they're giving you annual interest. So at time 0, you deposit the principal. After 1 year, this would be the second term, you would get the principal plus the principal times the interest rate, or the principal times 1 plus the rate. The second year, you would get what you got the first year times 1 plus the rate, or the principal times 1 plus the rate squared, and so forth. So notice that you get a general formula where t is time, and after a certain number of years, the money you would get back would be the principal times 1 plus the rate to the power of t, t being time. Then we have the case of interest compounded n times per year. So compounded interest more than once per year has a different formula. Notice that the principal is invested, but the interest is paid n times per year. So then R over n is the interest paid every compounding period. Since every year we would have n periods for t years, we would have n times t periods. So that helps us derive the formula for the amount as equal to the principal times 1 plus r divided by n to the power of n times t. So next we have example 3.10, and it says 1,000 euros is invested in an account paying compound interest at a rate of 6% per annum. Calculate the amount of money in the account after 10 years if the compounding is A, annual. So annual compounding is simple, right? It's just going to be the initial amount, 1,000, times 1 plus the rate, which is 6%, that would be 0.06. And because it's 10 years, this would be to the power of 10. So this is going to equal, in euros, it's going to be 1,790.85. For B, it's quarterly, so it would be the same formula, but we would have to divide by n and also multiply the 10 by n. So this would be 1,000 times 1 plus 0.06 divided by 4. That means 4 times a year. And this to the power of 40, right? So this is going to equal, in euros, let's see, 1,814.02 euros. For C, it would be monthly, so that means 12 times a year. So it's the same thing again, 1,000 times 1 plus 0.06 divided by 12 to the power of 120, or 12 times 10. And this was going to give us, in euros, 1,819.40 euros. So next we have example 3.11, and it says you invest 1,000 euros at 6% per annum, compounded quarterly. How long will it take for this investment to increase to $2,000? So this would be then that 1,000 times 1 plus 0.06 over 4, because it's compounded quarterly, to the power of 4 times the number of years. When is this going to equal 2,000? That's the question here. So if we do a little bit of expansion here and simplification, notice that we can divide by 1,000, and then we can add this in here, and we're going to get 1.015 to the power of 4t is equal to 2. So here we would have to solve this for t. What we'll do is that we'll use the GDC, and we're going to graph y equals 2 and y equals 1.015 to the power of 4x, and we're going to find their intersection. So here we are with the GDC, and notice that we have plugged in the functions that we just mentioned, y equals 2, and the second one would be y equals 1.015 to the power of 4x. So let's graph that, and there we can see that they have an intersect. So let's just calculate that. We go to second, calculate, and then intersect, option 5, and it's going to say first curve, yes, second curve, yes, hit enter, and there it is. Time would be 11.638881. So that's about almost 12 years, so 11.63 years. And we can round it to 11.64 years, so that's the time it would take. 11.64 years. So here we are in example 3.12, and it says you want to invest 1,000 euros. What annual interest rate is needed to make this investment grow to 2,000 euros in 10 years if interest is compounded quarterly? So this is very similar to the previous example. Notice that it would be that we want 2,000 to equal 1,000 times 1 plus the rate, which is what we find, compounded quarterly, so that's 4 times a year, and in 10 years, so that's 4 times 10, 40. So then we would get that 1 plus r over 4, and this to the power of 40 is equal to 2. So 1 plus r over 4 is equal to the 40th root of 2. And then we would get that r is simply going to be 4 times the 40th root of 2 minus 1. And we can plug this in the calculator, and we're going to get something like 0.0699. So we could say that you need an interest rate of about 7%. Now, of course, you can test this out by plugging it back in here, and you will see that if you plug in 7, or I should say 0.07 for the rate, you're going to get a number that is a little bit above 2,000 euros. So we can talk a little bit about population growth, because the same formulae can be applied when dealing with population growth. So example 3.13 is just about that. So the population of, I'm going to say this wrong probably, Baden in Austria grows at an annual rate of 0.35%. The population of Baden in 1981 was 23,140 people. What is the estimate of the population of Baden for 2025? So notice that this is 44 years, so T is going to be 44. So here we can say that the population, we're not talking about amounts anymore, so the population is going to be equal to 23,140 times 1 plus the rate. Now be careful here because this is 0.35%. So we have to add 2 more zeros to this to the left. So it would be 0.0035 and this to the power of 44. So we plug this into the calculator. We're going to get approximately 26,985. So that means that the population, or the estimate of the population for Baden in 2025 would be 26,985 people.